In this video, we will answer the questions from the worksheet about subspaces. For each of the first question, the question is determine whether the following sets are subspaces of the given vector space. For example, here, whether S1, the set of three-dimensional vectors such that x minus 3y plus 7z is equal to 0 is a subspace. Okay. If they are subspaces, find their bases and dimension, and if they are not, then find an example that shows that the set either is not closed under addition or scalar multiplication. Okay, so let's start. This is a set of vectors in R3 for which x minus 3y plus 7z is equal to 0. As we have discussed many times in class, the three-dimensional vectors given for which this condition is given, we can visualize them. This, everybody should know by now, that represents a plane that passes through the origin, and we know, we have proved in class, that planes that pass through the origin are subspaces. Okay, so one way to do it is to express this as a span of vectors in R3. So from here, from x minus 3y plus 7z is equal to 0, x is equal to 3y minus 7z, okay? And now the vector x, y, z. So once you have found the relationship between the parameters, go back to the general vector, and instead of x, I have 3y minus 7z, y and z, which is equal to y, 3, 1, 0, plus z, negative 7, 0, 1. And as we have expected, there are only two vectors in the basis, because a plane is spanned by two vectors. The dimension of the subset, the dimension of this plane, is just 2. So since S1 can be expressed as a span of vectors in R3, S1 is a subspace. Okay, basis of S1 is 3, 1, 0. The set consisted of these two vectors and negative 7, 0, and 1. Its dimension is 2. Okay, if we have to prove that the three conditions of this set, the three conditions that make this set a subspace, are satisfied, if you have sub-questions like this, show that the zero vector is in the set, and so on, that it is closed under vector addition and vector multiplication, we can also do that. That's not very difficult. Show that the zero vector is in S1, okay, while the zero vector is 0, 0, 0, and this belongs to S1 indeed, because 0 minus 3 times 0 plus 7 times 0 indeed is 0. 2. Let two vectors, x1, y1, z1, be in S1, which means that x1 minus 3y1 plus 7z1 is equal to 0, and let another vector, x2, y2, z2, be in S1, which means that x2 minus 3 times y2 plus 7z2 is equal to 0. Let's call these vectors u and v. The question is now, is u plus v in S1? Well, u plus v is equal to x1 plus x2, y1 plus y2, z1 plus z2, which is equal, and now the question is, whether this new vector, for this new vector, this condition is satisfied. So that means the question raised is whether x1 plus x2 minus 3 times y1 plus y2 plus 7z1 plus z2 is equal to 0. And yes, this holds. Why? Because if we drop the parentheses here and group them, we have x1 minus 3y1 plus 7z1 plus x2 minus 3y2 plus 7z2 is equal to, well, this linear combination is 0 because of this condition here, and this linear combination is 0 because of this condition right here, and 0 plus 0 indeed is 0. Hence, S1 is closed under vector addition. And finally, in order to show that it's closed under scalar multiplication, take the general vector u from S1 and multiply it by a constant k, or c, let's say c times u is equal to cx1, cy1, cz1. And now the question is whether this is in S1. When would this vector be in S1? If the condition, the first element minus 3 times the second element, the first entry minus the 3 times the second entry plus 7 times the last entry is equal to 0. So let's check whether that holds. Minus 3 times cy1 plus 7cz1 is equal to, well, I can factor the constant scalar c here, x1 minus 3 times y1 plus 7z1 is equal to c times 0, because this linear combination here is 0, and that indeed is 0. Which means that c times u indeed is in, so it implies that c times u is in S1, which implies that S1 is closed under scalar multiplication, which means that S1 is a subspace. Question number B. We're dealing with three-dimensional vectors for which the following is satisfied. X minus 3y plus 7z is equal to 1. And we know that this equation represents a plane that doesn't pass through the origin, and because of that fact, this cannot be a subspace. So this subspace fails any of the three conditions. Okay, it's not the zero element is not here, the zero vector is not here, sorry about that. It's not closed under vector addition nor under scalar multiplication. So the zero element is not the zero vector. I keep on saying it, element. The zero vector is not in S2 because 0 minus 3 times 0 plus 7 times 0 is 0 and not 1. So as you can see, this condition is not satisfied, which means that the zero vector is not in S2, which means that S2 is not a subspace. If you're asked on the test, determine whether this is closed under a vector addition, take two vectors from S2, let's say 1, 0, 0, and V 0 to 1. So 0 minus 6 plus 1 is 1. Okay? But now u plus v is equal to 1 to 1. And as you can see, this vector is not in S2 because 1 minus 3 times 2, I follow this condition here, plus 7 times 1 is equal to 1 minus 6 is negative 5 plus 7 is 2, so it's not equal to 1, which means that S2, sorry, is not closed under vector addition, which means that S2 is not a subspace. This is the same, S2 is not a subspace. And 3, in order to show that this is not closed under scalar multiplication, again take any, let's say this vector right here and multiply it by I don't know, 2 times u is equal to 2, 0, 0. And now we check, we determine whether this condition is satisfied. 2 minus 3 times 0 plus 7 times 0 is equal to 2, which is not equal to 1, as the condition have stated, which implies that S2 is not closed under scalar multiplication, and implies the same thing, S2 is not a subspace. So let's just make sure that we understand. If the question is solely determine whether S2 is a subspace, you have to show that one of the three, either the two closures are not satisfied or the zero element is not in the set. If the question specifically asks you determine whether the zero element is in S2, or show that the S2 is closed or not under vector addition, and the same thing, determine whether S2 is closed under scalar multiplication or not, then you have to go through each of these steps. Okay, we are still in R3, and I have x minus y is equal to 0. This set here is a subspace because this represents a plane. Plane goes through the origin. We can show that the zero element is in S3 because the zero element is 0, 0, 0. So I take x and y and I check whether x minus y indeed is 0. So that's okay. Take two vectors in S3. What would that mean? That would mean that x1 minus y1 is 0 and x2 minus y2 is 0, and then add them. U plus v is equal to x1 plus x2, y1 plus y2, and z1 plus z2. And now the question is whether x1 minus x2, sorry, plus x2, the first element, the first entry minus the second entry, y1 plus y2, whether it's 0. And this indeed is 0. Why? Because x1 plus x2 minus y1 minus y2 is equal to x1 minus y1, and this is 0 from here, plus x2 minus y2, and this is 0, so 0 plus 0 indeed is 0, which means S3 is closed under vector addition. And the third condition, take any constant scalar c times u is equal to cx1, I'm dealing with this vector right here, cy1, cz1, and indeed is in S3 because cx1 minus cy1 is equal to c x1 minus y1, which is c times 0, which is equal to 0. So as you can see for this vector, and this condition here, that the difference between the first and the second entry 0 is satisfied, which means that S3 is a subspace. And how are we going to figure out its dimension or the basis? Well, if you look at the condition x minus y is equal to 0, that means nothing else but the first two entries are basically the same. Go back to the most general vector here, x, y, z in R3. That's equal to x, x, z, because y is equal to x. Oops, sorry about that. Because y is equal to x, I write x instead of y, and this is 1, 1, 0 plus z 0, 0, 1. So the basis for S3 is the set 1, 1, 0, 0, 0, 1, and as we have expected, the dimension is 2 because at the very beginning we said that this represents a plane for the origin. Okay, in this problem here I told you that you should be ready somewhat to recognize you should be ready to recognize whether a certain set is a subspace or not, and we discussed why this would not be a subspace. Okay, make sure to understand that the 0 element indeed is in S4 because the 0 vector is just 0, 0, 0, and for this vector the product of the first two entries is equal to the square of the last entry. So the 0 element is in S4, but S4 is not closed under it's not closed under vector addition. Let u be 1, 1, negative 1, let's say, and this is in S4. Make sure to check. So 1 times 1 is equal to negative 1 squared, 1 times 1 is 1, and negative 1 squared is 1. And the vector v I don't know, 1, 4, negative 2, let's say. So 1 times 4 is 4, negative 2 squared is also 4. Okay, in that case, u plus v. So add these two vectors. This is 2, 5, and negative 3. And this is not in S4 because 2 times 5, the product of the first two entries in this new vector, is not equal to the square of the last entry, which means that S4 is not closed under vector addition, which means that S4 is not a subspace. And this set is closed if the question is determined whether this set is closed under a scalar multiplication or not. It is closed under scalar multiplication. Why? Because if I multiply x and y times a constant c, right, then the product of cx and cy would be c squared xy is equal to, and here I'll have to square cz, which would give me c squared z squared, and then that would be equal. So let's show that. Let some vector w be equal to xyz, which indeed belongs to S4, which means that xy is equal to z squared for this general vector, and then multiply w by c, you get cx, cy, cz. And now the question is whether this vector is in S4. And when would it be in S4? If this condition is satisfied, the product of the first two entries is equal to the last entry squared. So Cx times Cy, is it equal indeed to Cz squared? So whether this equality holds. Well, this is C squared xy is equal to C squared z squared. And since I can cancel this, I come to xy is equal to z squared, but that holds, that's true from here, because w was taken from S4. So indeed, any constant, any real number times w stays in S4, which implies that S4 is closed under scalar multiplication. That doesn't mean, it doesn't change the fact that S4 is not a subspace. It just means that S4 is closed under scalar multiplication. Okay, the next problem, we're still in this set here. Three-dimensional vector for which the absolute value of x is equal to the absolute value of z. The zero element obviously is in, you can do that as an exercise, so let's check first the vector addition. So take two entries take two vectors from S5, let's say 1, 0, and -1. Absolute value of 1 is equal to absolute value of -1. Let's say that this is the vector u. This is in S5, and w is equal to the vector 2, 5, 2. And this vector is in S5 because absolute value of 2 is equal to absolute value of 2. Okay, now the question is whether is u plus w in S5, and the answer is no, because u plus w is equal to 3, 5, 1. If you add these, right, 1 plus 2 is 3, 0 plus 5 is 5, -1 plus 2 is 1. And as you can see, absolute value of 3 is not equal to absolute value of 1. Which means that S5 is not closed under vector addition, which implies that S5 is not a subspace. Okay, the thing is that this set is closed under scalar multiplication, because any constant multiplied by x will be equal to the same constant multiplied by z. Okay, so take any let the vector v, the general vector from S5, x, y, z, be in R3. That means that this condition is satisfied for this vector. Then c times v is equal to cx, cy, cz. And now I'm checking whether absolute value of x, c times x, is equal to the absolute value of c times z. And this indeed is true, because absolute value of c times the absolute value of x is equal to absolute value of c times the absolute value of z. So since these two are equal, you can either cancel these or cancel these. You'll get 1 is equal to 1, which is true. So S5 is closed under scalar multiplication. Okay, so now we move towards the vector space of polynomials. This vector space here deals with cubic polynomials, okay, such that the cubic polynomial evaluated at 1 is equal to the second derivative of the cubic polynomial evaluated at 1. Okay, so let's take the most general vector in P3, right? That's a cubic polynomial, so ax cubed plus bx squared plus cx plus d. Okay, from here p of 1, if I evaluate this vector at 1, I would just get a plus b plus c plus d. And now this has to be equal to the second derivative of p of x evaluated at 1. So let's find the second derivative. First I'm going to find the first derivative, 3ax squared plus 2bx plus c. And now the second derivative is 6ax plus 2b. And from here, the second derivative evaluated at 1 is 6a plus 2b. So now these two have to be the same. Sorry, so p of evaluated at 1 has to be equal to the second derivative evaluated at 1, which implies that a plus b plus c plus d is equal to 6a plus 2b. And from here I can see that I can express either c or d in terms of the other parameters. So let's say d is equal to 6a plus 2b, and now I bring these terms on the right hand side, so minus a minus b minus c, and from here d is equal to 5a plus b minus c. Okay, once I have this relationship between a, b, and between d and a, b, and c, I will go back to the most general polynomial, and then I will express p of x as ax cubed plus bx squared plus cx, and now instead of d, I write the expression that I found in terms of a, b, and c plus 5a plus b minus c. Now we have done this practice so many times. Okay, express this in terms of parameters. So factor a and you get x cubed plus 5 plus b, you get x squared plus 1, right? And finally in terms of c plus c, x minus 1. And I get 3 cubic polynomials, each of them from S6, right? That span x6, so you get the basis of S6 is x cubed plus 5, x squared plus 1, and x minus 1. Since S6 can be expressed as a span of cubic polynomials, we conclude that S6 indeed is a subspace, and the dimension of S6 is 3, because I have 3 vectors in the basis. Okay, so here we deal with quadratic polynomials, such that the polynomial, basically all the polynomials evaluated at 0 are 1, their value is 1. So if you think about the general polynomials, right, p of x is equal to ax squared plus bx plus c, for which this is satisfied, where p of 0 is 1, p of 0 is what? Is 0 times, it's a times 0 squared plus b times 0 plus c, from where I just get that c is equal to 1. Okay, so basically this is another way to write down that S6 is the set of all the quadratic polynomials for which the constant term is 1. Okay, that's what we got. But this is not a subspace because none of the conditions of the subspace are satisfied. First, the 0 element, the 0 vector, is actually the number 0, and I can see that, right? We said that in the quadratic polynomial vector space, the 0 vector is just the number 0, and 0 is not equal to 1. 2, take two vectors from this set, okay, so take any two quadratic polynomials with constant term 1. So let's say u is equal to I don't know, x squared plus x plus 1, and v is equal to 2x squared plus 1. Okay, both of them are in S7 because both of them evaluated at 0 will give you 1, or in other words, both of them have constant term 1. But u plus v is equal to 3x squared, so I just add them, plus x plus 2. Let's call this polynomial, let's say P3, but P3 evaluated at 0 is 3 times 0 squared plus 0 plus 2, which is 2, and not equal to 1, or simply the sum of two polynomials in S7 don't have a constant term 1, but a constant term. So this is one example where they don't have a constant term, they don't have constant term 1. In this particular case, it's 2. So S7 is not closed under vector addition, and this is another reason why this is not a subspace. And condition number 3, okay, let's take this u here and multiply it by the number 2. 2 times u is equal to 2x squared plus 2x plus 2, and as you can see that the constant term is 2, which means that this polynomial evaluated at 0 will give me 2 and not 1, which means that S7 is not closed under scalar multiplication. Okay, the failure of any of these three conditions is sufficient to show that S7 is not a subspace, but we go over all of them in case the question on the test or on the final is actually going through each of these and checking whether they're satisfied or not.